Hi class. Our first lab is to measure the density of coke and water. In this lab, we will practice how to do some measurements. The amount the quantity we will measure is about the volume and the mass, right? And then we know that the density equal to the mass over volume. So according to that, you can see if we rechange these equations, we can write that as mass equal to density multiply the volume. And from here, we know the mass and the volume are linearly proportional. So because of that, we can make a graph of here, like this one. Here will be our mass. Here will be volume. And you can have a linear relationship. And the slope will be your density, right? So we will practice those things today. Let's look at some fundamentals during the measurement. The first thing is precision. Precision, by definition, that's talking about how close for your measurement to each other, right? So for example, you have a measurement, let's say you measure the volume of water, use pipette to take, you try your best to have a volume of 1.23 milliliter. Then you have another one is 1.23 milliliter, and another one 1.25 milliliter. And from here, we can see those values are very close to each other. So this case, we will see you have a very good precision for your measurement. But accidentally, if you have a value, which will be here 3.12 milliliter, then this we will consider them as outlier. So this one we have to discuss if we are focused on the precision. But for our experiment, since the volume is the one we would take to the flask, so either volume will be okay because every volume are corresponding to a mass. As long as those volume and the mass form a very nice linear relationship, they are okay, right? So from here, we can see the second one, we look at the standard deviation. That means the whole spread of your data. Like in this case, you have the first three data. They are very close to each other. So we will say the standard deviation will be very small, but if we include this one together, then the standard deviation will be big, right? So that's why we will consider this as the outliers. Now, second concept, we will look at that as accuracy. So accuracy here by definition is the closeness of the measurement to the reference value. Here we talk about the reference value. Often we call that as true value. Now the true value is, for example, if we have a piece of metal and that one has a mass, right? And the true mass is what? And our measurement, how close to the true mass. So that's what we will say. That's talking about how accurate your measurement is. However, in many cases, the true value is not available. Then how can we measure our accuracy if we don't know these true values? In this case, we have to do multiple measurement. Then we will take as the average. So the average, you see that we can use the central or typical value in a data set. We will average them, for example, if you have a number of N1, N2, N3, N4, and so on and so forth. total of n. Then this case, we will add them together. So the average, we normally use a bar in front on top of that equal to, here we added all those numbers ni, so I equal to 1 to n, and then divided by this n. So this will be the average. So we will assume, since your data, your measurement, it will be go to either, so this one's a true value, your data probably scatter around this true value. Some will go smaller, some go bigger. So average will close to this one. Now, the more data points you have, average, so those error will be canceled out, the more close to the true value. So that's how we will ask, normally when we do the measurement, we will do multiple measurements and take the average. So we consider the average as a true value. In this case, the still might not be the true value because that depends on how accurate your value is. So this value, we will call that an acceptable value. So in other words, we will talk about your accuracy is how close your measurement is close to the acceptable value. Okay. So as I said, linear regression earlier, I mentioned that this one can show the linear relationship between the two variables. We generate for the linear relationship, we have a general equation called y equal to mx plus b, or we can write as y equal to ax plus b, right? In this case, m or a are slope, and b are intercept, right? So if you make a graph of y versus x, you should have a straight line, and the slope will be the m, right? So in this case, to do those linear regression, and Microsoft Excel program, it's really, really useful. That depends on which computer you use or which software you have. If you don't have this Excel, you probably can use Apple's. We have a number, right? That's also a program allow you to do the linear regression as well. Okay, let's see. Now, during the measurement, we will have always involve the significant figure. Now, these significant figures, that tells the degree of confidence in the accuracy of a measurement when you do the calculation. For example, if we measure the volume, so for example, we measure the water, the volume you tell 1.0 milliliter. That means your value, we only this one is accurate. And this one's the estimate. So this one, normally you have some plus minus, something like that. So this one's accurate. But if you have another measurement, like this one, then both are accurate. But this one is the estimate. So the more decimal numbers you have, that means your numbers except the last one, all other number of the accurate, that indicate you have a higher level of confidence about your data, right? So we can use another examples here. So just like I said in the lecture, if you try have a ruler like this ruler here tells roughly about 1 inch, right? So this is the inch. You try to measure the length of, say, a coin. So you have a coin like this. Then you can only guess that one roughly from here to here. You say, okay, this one's a 0.4 inch. Then 0 is accurate, but this one's estimate because you can estimate it to 0.5, something like that. But if you go by somewhere like if we use another ruler here to measure that, we will say centimeter, 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 some like 1, 2, 3. So this case you can do say 1.2, so 1.2 centimeter. Then one will be accurate. So we know this size is at least one more than 1 centimeter in diameter for this case. But if you can have further one like divisions, use the millimeters, then you can do further right measurement. For example, 1.23 centimeter. Then these two will be accurate. So you can see that the more number you have, you are more confident about the numbers. Okay, so more examples shown here. You see the when the same object with different balance. So we in the lab we have two kinds of balance. One we will call analytical balance. Analytical balance typically provides the numbers like 4 decimals of that. So that will be have the you see here confidence level plus minus this 0.0001 grams. So you can always have that. So this tells you whenever if you measure the mass or weight using the analytical balance, you have to record the 4 decimal numbers. Even this one as 0, for example, accidentally your values of the mass is 1.1000 gram. Then on the balance will clearly show these values. You have to write exactly like this number, not write as 1.1 gram. If you write this one, indicate this one is the estimate and this one is true value. You can see those two numbers have even absolute value are equal when you do the calculation, but they have completely different meaning. A lot of balance we have that we have a pan balance or top loading balance. This type of balance will not have that high significant numbers given to you and often provide like this one. So when you record that, you can only record about this one. Now, even just for those two numbers, you can see here, and they have different significant numbers and they show different level of accuracy, right? So often we have this plus minus value. So in many cases, we will drop these plus minus values, right? So because that one here, we assume some will be plus minus, say something like 1 or sometimes it's 5. So, but those are the very, very small, so we normally don't write them. Now, here, talking about the significant figures, we will follow the rules how to count the number of significant numbers and how to calculate those things using the significant number, right? So here we will say what number are significant. So you see here, all non-zero digits are significant. For example, like 1, 2, 3, and here, there are 3 significant numbers. If non-zero, remember non-zero, all are significant. Now, then we will look at the zeros. Zero between non-zero digit are significant, like this 0. That's a significant. So total 5 significant figures. And 0 to the left of the first non-zero digit are not significant. This apply for that. You see this one is significant. So we have 3 significant figures, but this 0 is not a significant. So even you have a 3 place, but we only count as 2. And then likewise for here, no matter how many 0 you have, those are not significant. You still have 2 significant figures. Now, so those are the apply for, you say this one, you can write 0, 0, 0. And for this number, you still have only 2 significant numbers, right? If a number ends in 0 to the right of the decimal point, those 0 are significant. That means like this one, 2.0 or 2.00. Those are the, this one only give you 2 significant figures, but this one's 3. The reason for that, like I showed earlier, the last one often is estimate. You have to keep this one to make sure to guarantee the numbers preceding those one are true value or accurate. So this number, you cannot drop them, right? Now, if a number ends in 0 to the left of the decimal points, so we talk about left of decimal points, then those numbers may or may not be significant. Example here, you can see like a 120 gram for this case. You can consider that as a, so if you write them, can consider as a two significant numbers, like this one was 3, like we have a decimal point here. We'll put this one. So it can be 3, can be 2, right? Now, what's the general rule we follow? How many number of significant number we should keep after our calculation? Now, first rule is never do round up of numbers during the calculation. You will do the rounding after you finish all the calculations, okay? So then we will say for the calculation, most of the cases we will do multiplication and division and addition and subtraction. For those two type of calculation, we have two general rules to follow. For the divisions and those things, you will count, look at the term or the numbers you try to do multiplication and divisions, how many significant number you have. You will always keep the number matched to the one with the smallest number of significant number, okay? So for example, here, we have 29.1143. This gives us a total of 6 significant number, right? And this one here, 25.0, so that's only give us 3. So this 3 is smaller than 6. So after the calculation, even you have this much number like this one, and here you say 1, 2, 3, 4, 5, 6, 7, 7 numbers. But according to the rule, we said you can only keep 3, right? So that's the number of this one. You need to round it to up to 3. That's 3 significant numbers. Now, when we do the addition and the subtraction, situation will be changed. So this case, the result must be reported to the same number of decimal place as the number with the fewest decimal place. Now let's look at the example here. This was 19.2 gram, and this was 0.4745 grams, and this 127 point gram. Now this one has a decimal, you see here, decimal point is here, right? So after you add it together, the results will be 146.6745. If we just look at this number, we know this one will be the last one will be estimated, or other will be accurate. But the question is this number here, one component before you do the addition, this one can only be accurate up to this level. So any others will not be accurate, no matter how much you added, even how accurate your number added to this one, since this one is inaccurate for here. So all other numbers after that is meaningless. So that's how you have to keep up to this level, right? Now let's look at the rules for rounding the numbers. Here, first of all digits to be rounded are removed together, not one at a time. So I can show you one example here. Let's say this one, 1.46174, like this. If we want to do the rounding, right? And then look at that. So if our numbers, we only keep the first two, like those cases. This example, let's say we keep the first one. Keep the first one. We will do that. We said that all the number we will round here, remove together. If we keep the first one, so the after rounding, this just write as 1, right? Others drop, just 1. Now, if you do step by step like this one, we go here, drop, so we have 7. After we drop this one, we have 1.462. And then this one we drop 1.46. If we round this one go here, 1.5. And according to the rules, 1.5 was rounded to 2. So you have different values, right? And if the leftmost digit to be removed is less than 5, the last digit return is not changed. So just like I use the number 1.46172, for example, this number. So this number we try to keep, right? And this one, you see here, the leftmost, this digit is to be removed. That's less than 5. So then that means this number will to keep is not changing. So that's how we give 1. Now here, if the leftmost digit to be removed is greater than 5, again we use the example as 1.46172. If we try to keep these two numbers here, so the leftmost will be 6 now. That one is greater than 5. So then this number will keep but increase by 1. So that will, after that, it will be 1.5, right? If the leftmost digit to be removed is 5, so this is 5, and at least one of the other digits to be removed is non-zero. So this applies, for example, 1.45. So 1.45, say this one is 108, for example. Okay, so this one is about the leftmost to be removed. That's a 5. Then there's at least one of the other digit is not a 0. So this case, like 8. That means this one is more than half of that. So this case, and you can see this one here, last return, that's 4, will be increased by 1. So we can write as 1.5. Right? Now, another thing here, if the leftmost digit to be removed is 5, and all other digits to be removed are 0, so this case will be applied for again, like this case, right? So we will look at that is this one here. You can look at the last digit return, so this will be returned. If that is even, we just write an even. But if that's a 1.35, like this case, this one's odd, we will keep them even, just increase by 1. So this will give 1.4. So those are the general practice or rules we use during the rounding the numbers. Now here are more practice, like those things, right? We will look at all those numbers provided here. We will keep them for 3 significant numbers. Like this one, 3, so the 3 will be kept, right? This one is the leftmost, that one is to be dropped. That one less than 5, so we drop them. So that's how we have 34.7. And this one number, we still keep the 3. And this number is leftmost to be dropped. So that's one 6, 6 greater than 5. So this one we will increase by 1. So you have 9. Again for the 3, right? And here leftmost to be dropped is 5. And there's a number which is non-zero. So this one we drop and this will increase by 1. So you have increased by 1. And again, this number here, you see, and this one's a 5, but here are 0. So we will remove that and keep this one. Again, this one, the 3. This one's a 5, right? And this one's odd. So we keep changing that to even. So you have this one, right? And here, we will look at the uncertainties. So all the measurement has uncertainty. That's how we mentioned earlier. For example, you record the values like 1.200 gram. So this one plus minus. This will talk uncertainty. For all the measurement, you will have some uncertainty associated. Now, this uncertainty associated during the calculations, the uncertainty can be scaled up or can be scaled down depending what type of calculation you will do. For the multiplication like this one, if you have a measurement of A and the R value is obtained by multiply this value by a constant of k. In this case, so we will assume this one here, this one is a standard deviation of the a, and this one here, the r, so this should be a, and this the r will be also amplified by the factor of k. Now, if you have a or b, right, you do simple addition or subtraction, then this one has a standard deviation of a, and this is standard deviation of b, so that won't be done by this way. So you can see that, right? Take a square, then take a square root of the both added together. But if you do the multiplication or division, and then this one will divide by these r values. And here we have this too, right? And if you take a logarithm, so that when we have this relationship or explanation, you have this relationship, right? Now, for the density of 12-ounce cans of Coke and Diet Coke, we know for the Coke and Diet Coke, they have different weight. We talk about weight. We can test them putting them in a water tank. Now, in the water tank, you can see, so this is the water, right? If you have a Coke, which is the Coke can, which is heavier than water, you imagine this can will be sinking at the bottom. But if the can is lighter, density lighter than water, then that will float somewhere like this way, right? And here is actually you if you click this link, that will tell the, so let's see. And you can see this one will sink to the bottom, another one float, right? Now for this experiment, you will see that we have 12 ounce those cans. Okay, so here are some measurement, like the volume will be 355, and for those Diet Coke, the same volume, but the total mass will be this one here. And you can see for the empty can, they both are 13 gram, and the volume of an empty can will be all the same. The difference about those regular Coke and Diet Coke, you can see this one has a sugar 39 grams. And in these many cases, we will put the sucrose and also fructose, because fructose is much sweeter than the sucrose. So that's how we will make this one and more sweet for the Coke. Now, another thing is this one, instead of add a lot of sugar inside, for the Diet Coke, we add aspartame. Aspartame is a dipeptide, right? This one is about, so I will show you, if we assume the sweetness of sucrose as 1, then the sweetness of aspartame, so is 180. So that's how you see you only need a small amount of this one. You will have a similar feeling about the sweetness from drinking the Diet Coke. Now, since there's not much sugar added to Diet Coke, that's how we call it that this one will not get a lot of weight for that, drinking this one. However, this one will cause headache or migraine. Some people will have that, okay? Now, here are the calculations. You can see we mentioned that the density equal to mass over volume. For both, we can easily calculate their mass divided by their volume, right? The volume. So you can see this one, regular Coke, the density is slightly greater than 1. So that's how you see that sink to the bottom. But the dicoke is less than 1. That's how this is float, right? Now, for this experiment, you will measure the density of water and the coke and the dicoke. So you will do 3 experiments. Now, back to the question we mentioned earlier, we talk about linear regression, right? This will be your mass. This will be your volume. For the linear regression, if you want to have a good result or acceptable, normally we ask you have 6 to 7 data points, right? So that 6 to 7 are acceptable. If you have less than that, then you cannot tell the overall trend about those data. For example, here, let's see this one. You have one dot. If you try to draw a line across this dot, you can go any direction, right? Like this. So one dot cannot determine the direction. However, if you have 2 dots, if you are asked to draw a line across those 2 dots, you have only one way to draw them, right? Now, since all the experiments we mentioned that will potentially have uncertainty, right? Errors. So we cannot determine those 2 dots are both are accurately measured. So you have to make a lot of experimental data. Say example, you have another experimental data, or go to this one here. Then you can draw the line. Say here you can have a line, draw a line like this, and you can draw a line like this, and you can draw a line like this. Here you have 3, so you have 3 slopes. So this we cannot trust either one. Any of that, you can see the data are not the same. So that's how if we can draw, we can collect the data, which is here. So mass again, volume, and then we have multiple data. In this case, you will draw a line, and this line will consider all those data points and allow this line cross most of the data points, allow some like this above or some like this one below. So the above or below can cancel out the error, but what determines the overall trend? So this slope, we will consider them as accurate. So like this one, I show you if you have a small number of data points, then your regression is not acceptable. Okay, so because of that, for here, we ask you to generate 5 data points. So now, so you needed to do 5 measurements. So in this case, you need to create an Excel file. So table like this, right? So we have this one here. For example, this one you said volume. This one's mass. Make sure to put the units here. Volume, we use milliliter, and the mass, we use gram. And so here, before we do any measurement, both are 0. We don't have any water. For example, here we will use water, measure water, right? You don't have water added to flask, and so the mass is 0. Now, so we will use a flask like something like this. Make sure you can weigh this first, then add later on. Or you can do another way to put this on the balance and tell that, right? Tell that arbitrary set this overall as 0. So when you add the water to that, the mass you take, that will be the mass of water you added, right? Now in this case, you see here you have 5, so give you total data points 6, include the initial 0, right? So in this case, you can use a pipette which can measure the volume accurate to 2 decimal. So we can say you added a 1.20. Make sure keep the 2 decimal. As I said, this number are very important. Then you measure the mass. Then you add another one to the same added to this one. So in this case, we can do It's the we added a lot of meal, a lot of milliliter to the flask. So total volume changing to 2.20 now. And you have another mass here. But don't just write it, then you added say 1 ml added. You don't write that. You will write it as a cumulative because this one show the total volume of water in the flask. You try to measure that, right? That's what show the real relationship. And then this case, you can add another, say, 1.2. So that will get it to 3.40 now, right? And so then you have another mass. Then this one here, then we added, say, 4.56. Then you have that. Then this one case, we get 6.53 or 51. Then this one. So you have those numbers. Now, notice that this way we have those table, we can make a graph, right? And here's the mass, and here's the volume, and this one give you the linear relationship, right? 0 included that, and then you have 5, right? Slope will give you the density. And during the regression, you can click that, that equation can show the slope as well as R square. So you may ask, what's the R square? R square is the value, R square is the value to show how good your data is. So if the R square, the value of R square, so is something greater than 0, so R square, and then less than 1 equal to 1. So if your number is more close to 1 than equal to, so this one equal to 1 are the best. Okay, so that from here you can see the smaller the number or more close to 0, the worse your data is. So if you have something number like R square, if R square less than 0.8, you can see your data is very scattering, right? So this is the one we do the linear regression. Now, by the same time, according to our definition, like density equal to mass over volume, you can expand this table, right? Expand this table, say, expand them. And using those mass divided by volume, you will have a lot of density or numbers. And all those densities, you can average them, right? Those show the how deviation, you can calculate deviation of those numbers and average them, get the overall of the density. That's the average one. And then you can compare this average density versus the one you get from the slope, see how close they are, right? So make sure, just to make sure, when you do the linear regression, you would use this one, y. So you can see you want, so you have a linear relationship for this one, right? Make sure y is the gram, so that's the mass, and x will be the volume. Make sure that, okay?